Hi everybody. So we finished our Unit 10 Organic Chemistry, and hopefully we feel like we have a pretty solid understanding of organic chemistry. We're not having a formal test on organic chemistry at this time. I just don't want to give you an online test right now. If we end up doing this remote teaching for longer, then we probably will have some sort of formal exam or assessment on organic chemistry. But for right now, we're going to move forward into Unit 11. So we're going to be moving on to the heat unit. So you should have seen on the Google Classroom, I posted this PowerPoint, I posted the notes packet, and I posted the practice packet. Again, you don't need to have access to a printer. If you'd rather just take notes on a separate sheet of paper, that's fine. If you have access to a printer and you just want to write the notes in the notes packet, whatever works for you in this. So again, we're moving on to Unit 11, heat. And we're going to start with our first lesson, talking about heat and energy. So there's a couple different types of energy that we focus on in this class. Obviously, there's more energy than is listed here, but the three big types of energy that we're going to talk about in this unit are potential energy, kinetic energy, and thermal energy. So potential energy is stored energy, and in chemistry, when we're talking about stored energy, we're generally talking about the energy that's stored in chemical bonds. That's where the energy is going to be stored. Kinetic energy is going to be the energy of motion. And then thermal energy is going to be the energy of random motion of atoms or molecules in a sample of matter. Okay, so heat is going to actually be an energy transfer process. And I know that energy is going to move from hot objects to cold objects. You know that if you touch something that's hot, you feel that, that warmth on your skin. You feel that heat transfer on your skin. So it's going from the object that's hot to your colder skin or your colder hand. And I measure this heat in joules, and if I forget what unit I measure things in, I can just go to table D on my reference table. And table D shows me the units for my most common measurements in chemistry. So again, this heat is always going to be an energy transfer from a hot object to a colder object, and that colder object will get hotter as long as those two things stay in contact with each other until these two things reach the same temperature, and we'll call that a thermal equilibrium. So if you have a glass of hot chocolate that you leave on your counter, that hot chocolate is obviously hotter than the surroundings, so your heat transfer is going to be from your hot chocolate to your surroundings or to the air. And if you put ice cream on the counter, okay, that ice cream is colder than the surroundings are hotter. So that heat transfers from the surroundings to your ice cream, and that ice cream gets hotter, and that's why your ice cream is going to melt. So when you place an ice pack on your skin, what's happening is it's not that the cold is going into your skin. Instead, if you have an injury, you tend to have increased blood flow to that area. It gets swollen, so it gets warmer. When you put an ice pack on that area, you're drawing the heat out of your skin because your skin will be hotter, and so heat will be transferred to that ice pack. And you know that ice pack eventually melts because it's getting hotter. So this would be an example of a type of question that I could ask about heat transfer. So take a second, read the question, and we'll go over it. All right, so here they want to know the direction of heat flow. So I've got this solution at a temperature of 60 degrees Celsius, and the room or the laboratory is at 22 degrees Celsius. So hopefully we figured out that heat's going to flow from the solution to the surroundings or to the air or to the room. Okay, it's going to flow out of the solution into the surroundings. So when we talk about temperature, temperature is actually the measure of average kinetic energy of the particles in matter. So it's the average energy of motion of my particles. It in essence tells me how fast are my particles moving. So if I have a lower temperature, that means I have a lower average kinetic energy and my particles are moving slower. If I have a high temperature, that means I have a higher average kinetic energy and my particles are moving faster. So if I see a question like this, take a second, read it, try to answer it. Okay, so whenever you see a question like this, they're asking me about average kinetic energy. And I know that average kinetic energy is the definition of temperature. So I can literally cross out the words average kinetic energy and rewrite this question with the word temperature there instead. And if I reread this question, now it says, in which sample of water do the molecules have the highest temperature? So the volume actually doesn't matter at all. It's just asking me which has the highest temperature. So that should have been answer choice A at 100 degrees Celsius. So if we're talking about energy changes during a chemical reaction, we're talking about a reaction being an exothermic process or an endothermic process. And we touched on this a little bit, I think last unit. So exothermic reactions are going to release heat energy. So exo, like exit, heat's going to be exiting the system, so it's going to be released into the surroundings. And if I were to write a thermochemical equation, which means I'm including my energy in my equation. I know energy is not actually matter, but if I want to include it in my equation, I call it a thermochemical equation, and I'll write that energy for an exothermic reaction on the product side, meaning after the arrow. This is because energy is always going to be released as a product. It's going to be released at the end of a chemical reaction. If I have an endothermic reaction, well, that means I'm absorbing heat. And if I were to write a thermochemical equation there, including my heat energy, my energy is going to be written on the reactant side, so before the arrow. And just as a note, exothermic reactions tend to be more stable because when energy is released, that's more favorable in terms of our universe. Our universe likes to release energy. It creates a more stable product. So these reactions, these exothermic reactions, are actually more likely to occur because they make a more stable product that has a lower energy. So we're going to use a new part of our reference table, a new table from our reference table today. We're going to look at table I, and table I is going to show me energy changes for very specific chemical reactions. And it's going to show me these changes in terms of this delta H. So hopefully we know from our math classes that this triangle means delta, and that's the change in something. So this delta H tells me the change in energy. We specifically call it the heat of a reaction here. So how much is my energy changing? So on table I, you'll notice that delta H is over on the right-hand side of the table, and it's measured in kilojoules. Now, delta H, the number is important here, but the sign is also very important. We can have a positive delta H or a negative delta H. A negative delta H tells me that heat is exiting, heat is leaving, heat is being released. So that's an exothermic reaction. A positive delta H tells me heat is being added or it's being absorbed. So that's an endothermic reaction. That's how we're going to read table I. So if I look at what's given here, they give me this first reaction and they tell me that the delta H is this negative 890.4. That's in kilojoules. So that tells me that this is an exothermic reaction. And if I wanted to write out a thermochemical equation, meaning I wanted to put those 890.4 kilojoules into my equation, they'd go on my product side. Now, I wouldn't actually write them as negative 890.4. All that negative sign tells me is that it's an exothermic reaction. I can't subtract energy. I can't have a negative amount of energy. So I change that to a positive, but that negative tells me that it goes on the product side of the reaction. If this was a positive delta H, I would write it on the reactant side of the equation. So for example, if I am looking at this question here, it says when C2H4 is formed, is heat released or absorbed? Well, I'm going to go to table I, and I'm going to look for a reaction where C2H4 is formed. So if it's formed, that means it should be on my product side. So I'm just going to go down the list, and I'm going to look for a reaction where C2H4 is on my product side. And I should see it right here. And I'm going to look at the delta H. And the delta H is equal to positive 52.4 kilojoules. So what's important here, determining if heat's absorbed or released here, is I'm looking at the sign of that delta H. And the sign of that delta H is positive. And positive means that heat's being added or absorbed. So this is an endothermic reaction. Okay, so go ahead and try this example here. Again, this is going to be very similar. I'm going to look for this exact reaction here. Okay, so I see it right here. And I see that my delta H is negative 393.5 kilojoules. So I'm looking at the sign, and the sign is negative. So that tells me it's exothermic, and heat is released. Now, if I look at a question like this, this says when C2H4 is broken down. So now if I'm breaking it down, that means it's on the reactant side. And if I look at my list here, I don't see a reaction where C2H4 is a reactant. But I can go to that same equation that I used before, and I can look at it in reverse. If I take this reaction and I reverse it, meaning I completely flip it, so now my C2H4 will be a reactant, and I'll have 2C and 2H2 as my products. So before I flipped the reaction, the delta H was this positive 52.4. When I reverse the reaction, I'm going to reverse the sign of delta H. So if going forward on our table is positive 52.4 kilojoules, going reverse would be negative 52.4 kilojoules. So again, I'm going to look at that sign. That's negative. Tells me heat is being released, or this is an exothermic reaction. So take a second and try this one. All right, so if I look, I don't have this exact reaction on my table, but I have it exactly in reverse. So if I look right here, I have this reaction flipped, and its delta H is positive 66.4. So if I reverse that reaction to match what the question is asking me, the delta H is going to be negative 66.4 kilojoules. Again, I'm looking at that sign. It's negative, so that's exothermic, and heat's being released here. All right, so we're going to bring this back to the mole because the mole is the soul, and we're going to add in some stoichiometry here. And this is going to be the last thing for today. We'll add in a little bit of stoichiometry. It shouldn't be too bad. I know you all tend to freak out when you hear the word stoichiometry, but I promise it's not terrible here. Okay, so this question says when 3.6 moles of carbon dioxide are made from its elements at STP, how much heat energy is released? Okay, so first of all, I'm going to look for a reaction. Oops, sorry about that. I'm going to look for a reaction where I'm making carbon dioxide from its elements. Okay, so I have two reactions where I make carbon dioxide and only carbon dioxide. I have this reaction here, and I have this reaction here. So I need to look at the reactants in these. It says from its elements. So I'm not going to use this first equation because this first reactant here is carbon monoxide, C&O. That's a compound. That's not elements here, so I'm not going to use this one. I'm going to be using the one beneath it. And I'm going to look at the delta H here. And that delta H is negative 393.5 kilojoules. So just like when we were in our moles unit and we did stoichiometry, the first thing I'm going to do is I'm going to write what I'm given. So I'm given 3.6 moles of carbon dioxide. And I'm going to multiply this by a fraction. I know moles of carbon dioxide has to go on the bottom to cancel it. Okay. And they want to know how much heat energy is released. And this heat energy is my delta H, and it's measured in kilojoules. So I'm going to put kilojoules on top. And I'm going to use the numbers from table I to complete this equation. So if I look in the reaction, what tells me moles are going to be those stoichiometric coefficients. So those are the big numbers in front of the compounds. The big number in front of this compound here, this CO2, if there's no number, that implies it's a 1. So for every 1 mole of CO2, I have this negative, my delta H, 393.5 kilojoules. So I canceled out my moles of CO2. Now I'm in kilojoules, which is what we want. So I take 3.6 times negative 393.5, and that should give me something like this, negative 1416.6 kilojoules. Last step is I need to do sig figs. I'm only given one number in the problem. I'm given this 3.6, which has 2 sig figs. So I need 2 sig figs in my answer, which would mean my answer is negative 1400 kilojoules. Here's the next one. Last one for today, slightly more challenging. Take a second. Okay, I'm going to tell you, you are going to need 2 fractions here and try to figure this out. All right, so we're going to be using that same equation here in this one. Okay, that same negative 393.5 kilojoules of heat energy. But now I'm starting with grams of carbon dioxide. So I have 144.6 grams of carbon dioxide. I'm going to multiply by a fraction. I know grams of carbon dioxide has to go on the bottom. And now if I look at my reaction, I'm not given grams anywhere in this reaction. Yes, there are G's there, but remember that's not grams. That stands for gas. The only numbers I'm given are the stoichiometric coefficients, and those are moles. So first, I have to convert this to moles of carbon dioxide. This is a regular mole conversion from way back in the mole unit. So I know that 1 mole of carbon dioxide is equal to the gram formula mass. So I go to the reference table. I see carbon is 12, oxygen is 16, times that by 2, that's 32. So 12 plus 32 should give me 44 grams per mole. So now I canceled out my grams and I'm in moles. And I multiply by another fraction. Moles of CO2 on the bottom. And now, again, I'm looking for heat energy, and heat energy is measured in kilojoules. So kilojoules on the top. And now I pull the numbers from the balanced equation here. So in my balanced equation, it's 1 mole of CO2. And my delta H, which is kilojoules, is negative 393.5. So now my moles of CO2 cancels, and I'm left with kilojoules. So I take 144.6 times negative 393.5 and divided by 44, and that should give me negative 1293 kilojoules. And I just double check my sig figs. I'm only given one number in the problem. It has 4 sig figs, so my answer should have 4 sig figs, which it does. So that's the end of lesson 1, and we'll pick up with lesson 2 on Thursday.